Good evening. Let's start with the next topic, basics of digital filter. So, what do you mean by digital filter and what are its primary function? So, digital filter, what is it? A digital filter, it is essentially a numerical procedure or algorithm that processes a sequence of input numbers to produce a second sequence with more desirable properties. Okay, what it says, we have seen that when we are talking about the digital signals, they are nothing but a sequence of numbers. So digital filters, they are capable of accepting those sequence of numbers and give you another sequence of number from where you can derive some information. Okay, so what are its primary functions? The primary functions include the noise suppression. If there are any noises, say for example in the ECG signal, if we have this power line interference, so in India we have 50 hertz and in the US we are having 60 hertz power line. So if the ECG signals they are being corrupted with this power line interference, then we can design a noise filter to suppress the power line interference. Then enhancement of selected frequency ranges, as we have been discussing that what happens is that we want to do some enhancements in the region. Suppose the common example is that EEG signal. Okay, so EEG signals, they are very weak signals, and since they are very weak signals, we might be interested in amplifying the signal before we go for some analysis. Or what you can do is that if you have this over here we have this enhancement of certain frequency ranges. So suppose I want to extract a particular frequency and then I want to amplify that frequency because it may contain some additional information. So we can use these digital filters to perform that task too. Okay, then comes the band limiting. So band limiting we have already discussed in digital filters. Before we pass the signal into the digital filter, we have to do analog to digital conversion, and at the input end of the analog to digital conversion we may have a an analog what do you call low pass filter. Okay, now so that is for restricting the this maximum frequency. Then once it is digitized and it comes to the digital filter, so we may have, say for example, as in the example of say uh, this heart rate monitoring. So what we do, we take the ECG signal, then we band limit the signal in the range of 16 hertz to 22 hertz. Okay, to extract the significant component of the QRS complex. Okay, then we process it further. So during that processing, what happens is that we get some peaks. Okay, and when we get some peaks, we identify those peaks and we find out the time period between the two peaks, and from that time period we find out what is the frequency, and from there we can say what is the heart rate. Okay, from the frequency. So band limiting can help us in extracting some information that is not possible in the normal time domain. Okay, so then the last one is the specific operations. So we can do some specific operations like say differentiation, integration, Hilbert transforms we can implement, and in this way uh, they are quite helpful. So digital filters, it has become quite ubiquitous in modern electronics, including your medical devices. Okay, so, how does a digital filter process an analog signal? We have already discussed. We will be having analog to digital conversion. Then we will be doing the processing within the digital processors, and then we will be having digital to analog converter. Okay. So, what happens in digital signal processing? Say, for example, you want to measure the body surface temperature. So, we have thermistors, which allows us to measure the body surface temperature. Okay. Now, once we have that, so we'll be getting some continuous time signals. Then we can see we have discussed about the impulse trains. These impulse trains, then they are multiplied. So after the multiplication, we get these points, right? We get the points over a period of time, and then we quantize it to get the digital signals. Now these digital signals, they are then processed. Okay, and the distance between these 2 points, it is given by capital T. Okay. Now, when we do that, what we have basically, we have this kind of yeah, what do you call, a sequence of numbers which can be easily transformed into the Z transform, and we get this kind of function. Now, if you generalize this function, we get this function. What is this? This is nothing but your Z transform equation, unilateral Z transform equation. Okay. So from here, so suppose if there is any signal small a n, then we can rewrite the equation as capital AZ equals to this one, and we can generalize this equation like this: capital AZ equals to summation of n equals to 0 to k a of n t into z to the minus n. Now suppose we want to find the Z transform of a signal represented by any sequence. Okay, say for example, we are given with this input xn equals to 12530. So over here what we get is that if we apply the Z transform, we get this. Now over here, if you see, there are three operations that are happening, and these three operations, they are the most important operations. Okay, what are these operations? These operations are, the first one is the Z inverse. Okay, the first one is the Z inverse. So what is that? This is regarded as a delay. What does a delay do? Delay holds the signal component for one clock cycle. Okay, then second is multiplier. You all know that what is multiplier. If you give an input to a multiplier which is having a multiplier, which is basically a multiplier of k, then we will be getting d, which is equal to c multiplied by k. Okay, similarly we have the adder. So these are the three functions that we have. Okay, now in this case, if you see um, what is happening over here, we are having, say for example, we are having x of n. Okay, so how I am getting to this? So h of z is nothing but, sorry, no, this is x of n. Yeah. So say for example, uh, this is h of z. Okay, and it is given by 1 plus 2 z inverse plus 5 z to the power minus 2 plus 3 z to the power minus 3. Okay, just for the sake of understanding how these different operators they are working. Okay, so I am taking this xz basically a an hz. So when I call it as an hz, then it becomes a transfer function. Okay, transfer function of a system. Okay, so what is this hz? Hz is nothing but yz by xz. Okay, and we get yz equals to 1 into xz plus 2 into z inverse into xz, and so on, right? So what does this mean? This mean that xn is going to an input which is having h of n as the transfer function or the impulse response, and then we will be getting the y of n. Okay, and this Hn, it is being given with it has been represented with these coefficients of 1, 2, 5, 3, right? So let's see, if I have to implement this uh, filter or realize this filter, how can I realize this filter? And if you see, I am having only three operators, A, B and C. I do not have multiple operators. I can only use only these three operators. Okay. So what it says is that if I am given with the xn, the first instance it is directly going to the output. Okay. In the second instance, what is happening? We are having z inverse and 2. So Z inverse is a property where the Z inverse operator, it holds the signal component for one cycle. Okay, so it is directly acting onto the input. So I have to apply the Z component before. Okay, then I have a multiplier of 2. Okay, then what I am having? I am having Z to the power minus 2. But I do not have any operator called z to the power minus 2. Okay, but I can write z to the power minus 2 as z to the power minus 1 multiplied by z to the power minus 1. So I have already implemented z inverse. So from here I will take another terminal and I will put another z inverse, and over here the multiplier is 5. So I am having a multiplier of 5. Okay, then in the next stage I am having z to the power minus 3. That means I'll be taking another z inverse. Okay, and I will be having a multiplier of 3. Okay, and I have not added anything till now, so I have to add this now to get the output. So these will all be added. So I will be getting the output by it. Are you getting my point? So these are the three operators, and the diagram what I made it over here, it is called the realization of the filter. Okay, so this is called the realization of filter, and you have just now realized a digital filter. How your digital filter will work, you have the architecture ready. Okay, one thing you need to remember, in my last classes, we have been discussing about this filters and all these things. We have discussed about poles and zeros, right? So you need to keep it in mind that the number of poles should be greater than or equal to the number of zeros to make the filter realizable. Okay, to make the in fact you can say to make a Gaussian filter realizable. Okay, if the number of zeros are higher, then the filter does not remain Gaussian. Okay, so for a Gaussian system you should have this number of poles greater than equal to 0. Okay, and for the stability, all the poles should be within the unit circle of the z plane, and in the Laplace plane or the s plane it should be on the left hand side, not even on the frequency axis. Okay, so what are the fundamental building blocks? We already discussed. These are the adders, multipliers and the delays, and how do they operate. uh, oh sorry, I forgot to tell you how do they operate. Okay, so how it is operating, that is an important thing. We have realized the filter, but we need to find out what is happening over there, right? So we are taking the same signal. Okay, so it doesn't matter that we'll be incidentally we'll be having these multipliers also in the same order. Okay, so this is the zeroth instance here. So first, what I will get over here, I will get 1. Okay, so this 1, it will come to this adder. Through this adders it will come. So at the first instance, n equals to 0, I will be having this 1 coming all through. So 1, in the previous instance, what thing it is holding? This z inverse, what it is holding? 0. There was nothing. Okay, then over here again it was 0. Over here again it was 0. Right? नहीं समझ में आया? क्या नहीं समझ में आया? In the 0th instance, when you are releasing this one, it has come over here. ठीक है, इसका previous instance में देखो क्या है? 0. This is for the first delay. In for the second delay, we have to go 2 places back. 0. यहाँ से 0 आया एडर. Okay. For the third one, you go another. What is there? Nothing. 0. So we will be getting 3 zeros. Okay. So you add these up. क्योंकि adder है, so we get 1. So I am writing over here 1. The output. Okay. 1. In the next instance, what is coming? 2 is coming. ये 2 इधर आ जाएगा. In the output, we got 2. Now this z inverse will release 1. Okay, previous instance में इसने hold किया था. Now it will be here. So 1 multiplied by 2, it will come over here. 2. In the previous instance, इसमें क्या है? 0 था. This 0 will come here. This 0 it will come here. Okay. So add this up. I got 4. Okay. Next, what is coming? 5 is being released. Okay. 5 will come over here. 5 से पहले क्या था? 2. 2 into 2 4. इसमें क्या है? 5 into 1 5. एंड ये 0 इधर आ गया. So 10 14. Right. Next instance में what you have? 3. 3 will come here. 3 से पहले 5 into 2 10. उससे पहले 2 into 5 10. उसके बाद 3 into 1 3. तो यहाँ पे क्या आया? 20 26. Right. Then after that 0. So from here we will be getting 0. Okay. So previous to that 3 into 2 6. Then 5 into 5 25. Then 3 into 2 6. So how much I got? 25 plus 6 31 plus 6 37. Okay. Then it is not the end. So this 0 will come. Here I will be having 0. The previous 0 will be released here. 0. Then 3 multiplied by 5 15. Then 3 multiplied by 5 15. So 30. Right. Next another 0 will come. 0 0 0. ओके, ये तीनों में जीरो आ गया, 3 मल्टीप्लाइड बाई 3 9. Next, if you give another input, what will happen? Everything will become 0. So check this by doing the convolution. You know na convolution. Do this and find out the convolution of this one. Use the matrix multiplication method, it will be quicker. And check whether we have attained the same thing or not. So this is how your system works. So basically whatever the input you are giving, it is basically getting convoluted within the system, and the process of convolution, this one, this architecture, whatever we have drawn here, this is the architecture to perform convolution within the okay. So let's move forward. So when we talk about this digital filter processing, there are two important things. The first one is the anti-aliasing filter, and the other is the reconstruction filter. Both of these filters, they are analog domain filters, but without the use of these two filters, the digital signal processing, it remains incomplete. Band limiting, it is being carried out by the anti-aliasing filter. It is a low pass filter, as I already told you, right? But over there, the gain should be 1. Why the gain should be 1? Can anyone tell me? Anti-aliasing filter, it should have a gain of 1. If it is having any gain, what does that mean? That means it will be changing the nature of your signal. Okay, it will be changing the nature of your signal, है ना? So you can think it like this. When you have a matchmaking, okay, so if you go and represent yourself either as very rich or as very poor, what you are doing, you are giving a misinformation to the other party. Okay, now while you are doing this, while you are giving a misinformation, there would be a problem at a later stage. The same thing happens over here also. Say for example, you are processing the ECG signal and you amplify the signal through the anti-aliasing filter. If you are applying any pre-processing amplifier and it is a part of your processing technique, it's okay. But technically your anti-aliasing filter will not have any gain. Okay, otherwise what will happen? It will either increase or it will decrease the amplitude of your signal. And when you process it, and when you are trying to analyze something, some disease condition from that signal, process signal, anti-alias process signal, then it will give you a misinformation. Okay, and the treatment would be incorrect. Okay, so you can see how the misinformation, it plays an important role. Okay, so you need to keep it in mind, both anti-aliasing filter and the reconstruction filter, both are low pass filter. However, the anti-aliasing filter, it should not have any gain. Okay. On the other hand, the reconstruction filter, it is also a low pass filter. If you see over here, it is also a low pass filter, and it is applied after the digital to analog conversion. Okay, so we will be coming to it, how it helps. Now first look into this thing. Okay, so anti-aliasing filter and the reconstruction filter. So if you see x of f, it should be 0 at frequencies greater than fs by 2. Okay, so for the it is and for the anti-aliasing filter, your equation is HAAF it is equal to 1 for modulus of F less than equal to Fs by 2 and it is 0 outside. Okay. So primary purpose of anti-aliasing filter is to prevent an aliasing. It allows low pass filter with an amplitude response of 1 within its passband. Okay, the filter's response is unity to ensure that the desired signal, which is band limited, passes through without any attenuation. Okay, if the amplitude response were anything other than 1, okay, the signal's original amplitude would be altered before it is even sampled, leading to an incorrect digital representation. Okay, whatever I told you. So basically, in layman's term, you can say that the anti-aliasing filter it acts as a gatekeeper, allowing only the valid frequency components to pass through, while completely blocking or attenuating frequencies above the Nyquist frequency. Okay? So after the digital to analog conversion, we have another filter, as I told you, the reconstruction filter. Okay, so the ideal reconstruction filter it is expressed in this form: yt equals to summation of n equals to minus infinity to infinity x of n sinc of t minus nt by t. Okay, so from where this term is coming? This term is coming because we are applying big filter. We are applying a big filter in the frequency domain. Okay, so over here, this capital T, it is nothing but capital T is equal to 1 by Fs. Fs was the sampling frequency. T equals to 1 by Fs. And here, if you see the in the reconstruction filter, your amplitude of the passing band it is capital T and it is not 1. In the case of anti-aliasing filter it was 1, but in the case of reconstruction filter it is capital T. Okay, so these are some of the properties of the reconstruction filter, so I am not going through this. Okay, so why we have this capital T? Okay, so sampling in the frequency domain, we are having, so sampling in the continuous time domain of a continuous time signal xt with a sampling period t and sampling frequency of this thing can be mathematically represented with this equation, right? So in the frequency domain, so what happens if we do the Fourier transform? So we have x of s, excess of f, which is equal to f of s summation of k equals to minus infinity to infinity capital X of f minus k of fs. Okay, now what is happening? The goal, what is the goal of the reconstruction filter? The goal of the reconstruction filter is to isolate the origin signal spectrum, the baseband, and remove the other copies, also known as images. Okay, this is achieved by passing the sampled signal through a through an ideal low pass filter which has a transfer function of h. Okay, for perfect reconstruction this filter should have a rectangular shape in the frequency domain. Okay, so the output of the reconstruction filter it is given by y of f. So y of f, what is it is? It is equal to hf into xsf multiplied by h of f. Okay, why? Because the output it is given by convolution in the time domain. So in the frequency domain it is the multiplication of the previous one x of s f sampled signal, this Fourier transform. Okay, and over here. Okay, so if you look over here, so our equation it becomes something like this. So what happens? So we have this excess f. It is represented with sampling frequency multiplied by original frequency of the analog signal component after anti-aliasing. Okay, so sample frequency multiplied by this one multiplied by h of f. Okay, now to make y of f equals to x of f, because it is the requirement, it is the requirement. So what will happen, we will be having this f of s and h of f should be equals to 1, because we want y of f equals to x of f. Are you getting my point? We want y of f equals to x of f. Why you want? Because whatever has entered into your digital processing system, you have just processed it and you want the same signal over here, until and unless you are providing some gain within the digital filter. Filter means basically the removal of the frequency components. Filter does not mean that you want to apply some gain. Okay, filter means it is just removing the frequency components, okay, or suppressing some frequency components. Okay, so your input and output, they should be same. Now since they should be same, and what we have to do, we have to keep this fs equal to h of f equals to 1. Okay, now when it becomes 1, when h of s, your transfer function of the system, it becomes 1 by fs. Now what is 1 by fs? We already discussed 1 by fs is nothing but your capital T. So what should be the gain of your reconstruction filter? The gain of the reconstruction filter should be capital T, and that is what we have seen. Okay, so this gain is essential for scaling the spectrum correctly. Okay, restoring the original amplitude of the signal's frequency components that were scaled up by fs during the sampling process. Okay, the reconstruction filter effectively performs the reverse operation of the sampler, bringing the signal spectrum back to its original form. Okay, so this is the main important point over here. The reconstruction filter effectively performs the reverse operation of the sampler, that is the sampling, bringing the signal spectrum back to its original form. Okay, now what happens? Okay, so suppose over here the green curve, it has become overlapped. So on the top you are having the green curve. So it is your original analog signal. Then we have some black dots you can see over here. So these black dots, they are the discrete time samples. Oh sorry, these black dots, they are the discrete time samples. Okay. Then we have the red staircase. This red staircase you can see. So these are the digital to analog output. Okay. So I already told you that when we convert digital signal to the analog signal, we get staircase signals. So these staircase signals, they look something like this. Okay. Then we have this blue dashed curve after the reconstruction. So blue dash curves, you can see it is nearly overlapping with each other. So this is how a uh, this gives you basically all the output starting from the analog this thing, then your frequency sample, so how it this amplitude samples, how it look like, then after the conversion into the analog domain, how the signal look like, and after the reconstruction, how the signal look like. So it gives you all this information in this same curve. Okay, so if you look into the spectral component, so this is the original spectral component. If you see, if you consider this as the Nyquist frequency, okay, so if you see over here, you get some positive frequency, and each positive frequency they are associated with negative frequency, so it has come over here. Okay, then when we have sampled the signal, if you see this frequency component, positive frequency component, it has got mirrored in the negative one. Okay, so by applying the this thing, this Nyquist frequency, we uh, try to stop this what do you call overlapping of these things. Okay. So lastly, reconstructors here spectrum after sampling. So after sampling, it goes over here. So we have already discussed previously. What happens is that when we go for the when we want to stop this aliasing, we have to confine the sampling frequency to the maximum frequency to the half of the sampling frequency over here, 500 hertz. Okay. Then after the reconstruction, what is happening? Again, we have to apply the same cutoff frequency. Okay. And by applying the same cutoff frequency, this additional frequency component, it is getting filtered out. Okay. Because what has happened? After sampling, this has been added. This frequency component has been added. So we need to remove this. So that removal, it is being done by this reconstructed filter. Okay. So the main what you call takeaway from here is that both anti-aliasing filter and the reconstruction filter, they are low pass filters. They have same cutoff frequencies, but the gain of both the filters are different for the reason what I have discussed few moments back. So importance of the number of poles and zeros, I already told you the number of poles should be greater than equal to the number of the zeros. Okay. For the stability purpose, all the poles should be within the unit circle and zeros can be anywhere on the z plane. Okay. For causality, I told you that you need to have the number of poles greater than equal to the number of the zeros. Then filter designing aspect I have told you. So the filter designing, it can be taken place by two methods. One is FIR filter designing method and another is IIR filter designing method. FIR filters means finite impulse response. So impulse response is HN. So finite means if the number of HN values they are limited, then it is called finite impulse response filters. And if you are trying to approximate the analog filters, then we get the IR filter where the HN, it goes up to infinity. Okay, and hence it is called infinite impulse response filters. Okay, because it is having infinite number of HN values. Okay. So a filter is considered proper when the degree of the numerator polynomial is less than or equal to the degree of the denominator polynomial. This condition is also known as n less than equal to m, where n is the number of zeros and m is the number of poles. So a system is causal if its output at any given time periods depend on its present and past inputs. Okay, so such a system is physically realizable. Okay, if a filter is improper, that means n greater than m, its transfer function would require differentiation of the input signal to produce the output. Okay, differentiation is a non-causal operation because to compute a derivative, you need to know a signal's value at a point in the future. Okay, so if you look into the Laplace domain equation, so y of s is something like this, and Laplace transform of a derivative, it is given by of xt, it is given by s to the power n xs. So a term like s square in the transfer function means second derivative in the input signal. So to compute a derivative at time t, so we need to know the signal's value at t and at t plus delta t, which is a future value. Okay. So during the computation, if you see, when we try to find out this, say for the this thing for the derivative of this one, we may say that why we will be taking the future value. We can do the derivation using the backward difference method also, where it takes the previous value. Okay, so that can be the one of the question. But the thing is that when we try to find out the uh, derivatives, it tries to find out the derivatives using both future and the past value, and then it tries to converge to the time period t. Okay, so it analyzes the derivative both at the using the future value and the past value, and then it tries to converge to the point t, which is the present instance. So if we do not know the future value, then we will not be able to find out the present instance also, if there is a derivative component associated in the transfer function. And in the numerator, if it is greater, you will be left with this extra s components. Okay, and if you are left with extra s components, it will make the system non-causal, and since it will be non-causal, your filter will become unrealizable in the physical domain. Okay. Another important thing, placement of the poles in the zero. Now we talked about this what do you call this transfer function, and we have seen that our numerator and denominator both are polynomials. Okay, so what happens if I have a 0 at z equals to sorry s equals to a, and I have a pole at s equals to a? It gets cancels out, and I should have h of s equals to 1. That means no gain, no loss. Okay, but is it possible to design such a filter in the physical domain? Why? Reason being, when we are talking about designing a system in the analog domain, if I say you use 1 kilohertz, 1 kilo ohm resistance, will it be a 1 kilo ohm resistance? It will have some variation. Okay. Similarly, if you want to use capacitor, it will have its own variation. So even though we are saying mathematically, we are calculating and we are saying that we can put one pole and one zero at the same location, and we will be managing like that. But technically, it is not possible. And what it does is that this slight mismatch in the poles and the zeros, zero it will be put to your amplitude value, it will be having low. If you consider the y-axis as the amplitude, it will be low, and just beside that you will be having a pole which is having a very steep thing. So you will be getting an unwanted what you call spike in your system. Okay, so in analog domain it is advised not to place a pole and the zero at the same location. So what happens if I place a pole over a zero, or a zero over a pole? When we place that, suppose we are having a 0, that means it is suppressing the output. If I place a pole over that, it is bringing the value to 1. That means no gain. That means the pole is cancelling the effect of 0. On the other hand, also it is true, if I have a pole, your amplitude will be very high, and if I place a pole over there, they will cancel each other and I will get an amplitude of 1. Okay, so that means if we place a pole over a zero or a zero over a pole. In either way, the pole and the zero they will cancel their effect. Okay, cancel each other's effect. So in Laplace domain, placing a pole over a zero or vice versa, it's not possible. Okay. On the other hand, in digital domain, once you have digitized the signal, it is possible. But then, why you want to unnecessarily increase your resources? Because putting one pole and one zero extra, it will increase your multiplier, delays, adders, everything. So your computational burden will increase. So if you have to cancel each other and you do not want to have any effect, then just remove that pole or the zero for which you want to suppress the this gain property. Okay. So this is what it has been told over here in all these slides. Yeah. Again, over here, let's take an example. We are having this z square equals to 1. Okay. So a system is causal if the impulse response hn is 0 for all n less than 0. The impulse response is the inverse z transform of the transfer function. Okay. So the for the hz z square plus 1, the impulse response it will be h of n, which is equal to delta n plus 2 plus delta n. Now, if we perform the this what do you call it? If you look into this term delta n plus 2 term, which is non-zero at n equals to minus 2, this indicates that the system has a non-zero output before the input is applied at n equals to 0. Getting my point? So it makes the system non-causal, and this is the mathematical definition of a non-causal system. So design and stability consideration, the same thing. So if you have any questions, any doubts, any